Okay, and so today we're on differentiation 2 and we are going to look at increasing and decreasing functions. Okay, so here we're going to look at increasing functions. And so this says that basically that a function f of x, so the y values, increase on an interval if for all those y values, as we move along the x-axis, the y values increase, they go up higher. We can see always for strictly increasing functions that they're always increasing is again on a curve. Here we can see that this one is an increasing function, but not strictly so, because here, if I go from this point here, A, just along to here, f of A and f of, if I was to call a point here, maybe C, then f of C would still be the same as f of A. Whereas here, at this point here, that's when f of B begins to increase. So this one is an increasing function, but not strictly, because we have some y values that are the same even as A increases, as the x values increase. We'll see the same now for decreasing functions. Okay, so here we have decreasing functions, again similarly to our increasing one. When it's on a curve, here we can see as the x values increase, our y values are constantly decreasing. So that's why it's a strictly decreasing function. Here on this picture here on the right hand side, we can see that as we move along the x values, as they're increasing, up until this point here, the y values are staying the same, but then they begin to decrease from here on in. So this one is a decreasing function because at no point is it increasing. So it's decreasing, but not strictly so, because for this part until here, they're remaining the same. Okay, so that distinction is important. So let's make sure that we get both of those, the box and the sketches, down for both increasing and decreasing functions. And then let's look at an example in relation to this question. Okay, so here we're given a function f of A to or, so to the reals, where x, the function is x minus 4 all to be squared, and it's a closed interval from 1 to 5, which means here the square brackets 1 is included and 5 is included. Here we see a roundy bracket are at 4, which means 4 is not going to be included. So here it says explain why f is strictly increasing on the interval 4 to 5, where 4 is not included. So if we look here and draw in two x values, one which we call maybe x1 and another which we call x2, and I'll just draw that in a different colour. So here we have x2, and then so we'll just look at their corresponding y values. So the corresponding y values here for x1 and x2, we'll call them f of x1, f of x2. We can see that f of x2 is greater than f of x1, as x2 was also greater than x1. So that's why it's strictly increasing here. 4 can't have been included there, because at 4 we can see that the curve is at its lowest point. So f of x1 and f of x2 would be equal as we are at this point here. So that's why our 4 is not included. So if we're to answer this question, we say that as f of x2 is greater than f of x1 for all, do you remember this symbol here, for all x1, x2, which are an element of this interval from 4 to 5, though 4 not being included, where x2 is greater than x1. We can see that again because it's moved along the x-axis, that f is strictly increasing on 4 to 5. So because this is strictly bigger than the other. Okay? If this symbol was included, then 4 would also could have been included in that, and it would have been an increasing rather than a strictly increasing function. Okay, so that's that part shown. And next then we're on to part 2. So here we're asked to define the largest closed interval on A on which the function is decreasing. So well, our closed interval begins at x equal to 1, and we can see all along here the whole way down the function is strictly decreasing, or is decreasing, sorry, and it goes all the way down to 4. And why? Because here is where it begins to change. And even if we were to test that out algebraically, if we had at x equal to 3.9, we would have f of x would be equal to 3.9 minus 4 all to be squared, which would give us 0.1 to be squared, which is 0.01. And if we went to 3.99 minus 4 all to be squared, we would have 0.01, and square that, we would have 0.001. So we're getting closer and closer to 0, but we're still going downwards. We're still decreasing there, okay? All the time, because obviously this number is much smaller than this number. So here our largest closed interval is going to be from 1 with our square bracket up as far as 4, again with our square bracket showing that both are included. And this is where, so writing that in maths then, we have, well, 1, 4 is our closed interval, our largest closed interval, where f is decreasing, as f of x2 is smaller than f of x1. We can see that here, even though x2 is bigger than x1, or where x1 is smaller than x2. Okay, and so we can't go more than 4, because we know at 4 is where it starts to increase again. So this is our widest or our largest closed interval where it is decreasing. Okay, so we know that when we differentiate a function, we get the tangent to the function at that point. Okay, and we can see here, so normally if we differentiate a curve, we get a linear function always. So here we can see that if the slope of that tangent to the curve is increasing, well then that function has been increasing. If the slope of the tangent is decreasing, is a negative slope, then equally the function itself is decreasing. So again, let's pause the video, sketch these curves and their tangents, and let's get the notes down, which basically says that f is strictly increasing because the slope is also a positive slope of the tangent line here, and likewise that f is strictly decreasing because our tangent line has a negative slope. Okay, so we're going to do this question here as an example, because basically the steps in the question give us the steps to investigate if a function is increasing or decreasing, and to find the range of values for which that is happening. So we get the derivative, then we solve the equation, we sketch the graph, and then we find the range of values for which they're greater than or equal to 0 if it's an increasing function, or less than or equal to 0 if it's a decreasing function. Okay, so let's have a look here. So the first thing that we have to do, we have our function g of x, which is defined as 3x squared minus 2x cubed. And so, well, g prime of x is going to be equal to 6x minus 6x squared. So here in part 2, we're asked to put this equal to 0 to solve for x. So we'll say g prime of x equal to 0 is 6x minus 6x squared equal to 0. Well, I can divide across by 6, which is going to leave me as x minus x squared equal to 0. The 6's will cancel out. And then the next part then, just to factorise out, here I have x, which is 1 minus x is equal to 0, and then putting each part equal to 0. So I have x equals 0 and 1 minus x equal to 0. So this is going to give me my two values for x. So that means 1 is equal to x. So now I can sketch my curve with both of those values for x. So here is a sketch of the curve here. Now, if I wanted to do a curve to sketch this quickly, I know already that my two values are 0 and 1. So there's 2 points that I know. Then basically, either way, I'm just going to, if I was doing an input box for that, I might put in x equal to 1 and x equal to 2. So very quickly, I'll just draw one of those just to. Okay, so that's our input box, but it's just basically we're going to number either side of the two values that we've been given here. Okay, so this graph is actually a little inaccurate because we should see at -1 that we're down here at -12, and likewise at 2 that we're bang on going through -12. Anyway, we're hitting it here, so this is the important part. So basically, we want to find the range of values of x for which g of x is greater than or equal to 0. So we can see that's this point here, okay? So let's just do that bit there in purple. And so we can see that this is happening between 0 and 1. But if we want to be sure and to test this out exactly as we did during functions, we might pick a number between 0 and 1. So if we pick 0.5, so we say g prime of 0.5 and sub it in. So that's going to give us 6 times a half minus 6 times a half to be squared. And we're going to see, will that give us a positive or a negative answer? 6 times a half is 3, and 6 times, well, a half squared is a quarter. So 6 times a quarter is 1.5. So 3 minus 1.5 is 1.5, which is greater than or equal to 0. So we know that it's definitely between 0 and 1. So we can say then the range of values for which g prime of x is greater than 0, greater than or equal to 0, is between 0 less than or equal to x, which is less than or equal to 1. So that's our answer there to part 4. So now we're asked to complete the sentence. So a function is increasing on an interval if g prime of x is greater than or equal to 0 for all values of x on that interval. So that's exactly what we have here. Okay, and so we have, they ask us for the range of values for which g of x is increasing, and so that's what we worked out there. Okay. Okay, so let's make sure that we get all of these notes taken down in examples and then onto Schoology for our learning check questions.